Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome back. We did acids and bases introduction last time, and this is from there. Just to review what we did last time, we said that if you have an acid, then it would, when it deprotonates, it goes to a conjugate base. A conjugate is only one proton different from the original acid or base. So if you take off one proton, it gets to the conjugate base. And we found out that certain things tend to give off a lot of protons, and so they're very, very acidic. So here, this is the pKa value, and the Ka would be 10 to the minus pKa, just like we did with pHs. So this will be about 10 to the 9 Ka, very, very high. Here the pKa for this molecule is 50, so the Ka is 10 to the minus 50. So we have a range here all the way from actually 10 to the 11 to 10 to the minus 50 Ka values. That is the acid dissociation constant. Can be 10 to the minus 50 for some molecules and about 10 to the 10 or 11 for some molecules. So you have a huge range. And comparing to water, certain things are way more acidic and certain things are way more basic. So the basic here is in blue, the acids are in pink. We talked about three types of acid definitions and base definitions, Arrhenius, Lewis, and Bronsted. Today we're going to look at how these are going to predict equilibria. What that means is if you mix a molecule from here and here, what's going to happen? So that's our inquiry for today. Acid-base equilibria. If you have an equilibria, you have to have an equilibrium constant. And so we are going to talk about that as well, K equilibrium. And well, the most important thing about K equilibrium, first of all, is the magnitude of the K equilibrium, how big it is, and is it greater than 1 or less than 1? If it's greater than 1, it goes forward, and if it's less than 1, it goes backwards. It can never be negative because K equilibrium is basically a ratio, something to something. So it's never negative, but it can be greater than 1 or less than 1. And that's what we're going to look at. If it's greater than 1, it goes in one direction, forward direction. Less than 1, it goes in the reverse direction. All right. Let's look at some examples. Now, I'm just going to talk about what we said in Gen Chem first. First, if you have an acid-base equilibria, we can write it down. Let's say this is your acid. A is going to be any one of these in the blue. And HA is any one of these on the top, which is an acid. And that is going to just go over, grab a proton, and all of these acids and bases, the pH only works in water, and pulls off a hydrogen and becomes H3O plus and A minus. And we would call the Ka for that, the equilibrium constant for that, as a Ka, which is basically your H3O plus times A minus over your starting materials, which is HA. H2O is 55 moles per liter or molar. For a liter water, the number of moles is fixed, so that constant is then inside the ionization constant, dissociation constant. Let's look at what happens when you have a base. So if you have any one of these blue molecules here, in this case, let's take the same A minus here as the base. And that too can dissociate. In this case, we call it hydrolysis. It lyses the water. Base hydrolysis. Kb, and therefore it's going to give you AH and OH minus. So Kb is going to be again products over starting material. So anytime you write the acid on top, you would write the OH minus next to it. If the OH minus is written on top, that's a Kb. If H3O plus is written on top, that's the Ka. It's one of the ways to identify them. So what we learned in Gen Chem is that when you have an acid-base equilibria and you add them up, as long as these are the same, I will just put 1 just to show you that these are the same system. You're going to have then these cancel and these cancel, and you would get 2H2O going over to H3O plus and OH minus. I'm sure you'd recognize this as just the dissociation constant for water, and that is Kw. That's the dissociation of water, or ionization of water. And when you add two equilibria, this is acid and this is base hydrolysis. When you add the equilibria, then you have to multiply the K's. So you add 1 plus 2. Over here, you are going to get over here Kw here. So you can see Ka times Kb is going to be this times this. This is Ka times Kb. And you can see these are going to get cancelled. It's going to be Kw, which is this. So we kind of proved that this is correct. And this, you did this before as well. I just wanted to, we're just going stepwise. So this is one of the very important tenets or concepts in acid-base chemistry, right? Ka times Kb is Kw. What does that mean? What are the implications? That means if the Ka is high, Kb will be low because it's going to be 10 to the minus 14. So whenever you have a strong acid, the conjugate base would be weak. Ka goes up, Kb has to come down because they are both linked to this through a constant. This is really, really important. So weak acid, strong base, conjugate base, or strong base, weak conjugate acid. That's a given. So Ka goes up, increases. Then Kb is going to be decreasing. And we can see that here as well. Ka goes up. Then the Kb is going, in this case is pKw. 14 minus pKa would be pKb. pKb will be going down. That is a very important concept. Another very important concept is if you have two different acid systems and you mix them together, what's going to happen? Is there going to be an equilibrium? In which case, what direction? That's another very important concept as well. So let's take two different acids. Let's say we have HA1, and that's going to go to, let's take an actual example. For example, let's take some very common acids and bases. Let's take acetic acid, and well, let's take these two acids and add them together. So HA1, let's say, is acetic acid. So let's say this is going to be CH3COOH. And let's say HA2 is going to be, I'm just going to put it in a different color, is going to be, let's say, you can take any acid, but let's take a very common one, ethanol. So if I write the dissociation reaction for that, CH3COOH plus H2O. H2O is just going to pick up that proton. That's all that it does. And that is going to give you CH3COO minus plus H3O plus. And we can do the same thing with this ethanol. Let's say you're mixing them to both. So you have an ethanol here, and you're adding water to that, and let's say this is a possibility, and that's Ka2, let's say this is Ka1. So that is going to give you just the deprotonated ethoxide plus the hydronium. And let's see what would happen if you mix these two acids. Let's look at the pKa's. The pKa for one of them is 4.8, pKa here is 4.8, and the pKa for this is 16. What does that mean? We know that the lower the pKa, stronger the acid. Higher the pKa, weaker the acid, but stronger the base. So therefore, if you have a weaker acid, you're going to have a stronger base. So stronger acid, weaker base. Because of the pKa values, we can predict this is your stronger base and this is your stronger acid. And obviously, the strong would like to react with the strong, right? The weak are just going to watch. The equilibria is this picking up a proton and going over here. So this is what is going to happen. So here, this is going to be the actual reaction where you will have an O minus, pick up the proton here, H3O plus, and go to a ethanol. And water. So this is going to be 1 over Ka2 because we are reversing the reaction. Basically what happens, your strong acid is going to dissociate and your strong base is going to pick it up. Now I'm saying strong and strong. These are all these acid-base equilibria. Whenever you have a Ka or a Kb, they are for weak acids and weak bases. So I should really say stronger weak acid. You got to be like below pKa 0 to be like really like HCl, HI, the strong acids that you learned. And group 7 acids, HCl, HBr, HI, and the HClO4 and H2SO4, HNO3. Those are the strong. Everything else is weak. Of the weak, of course, we have a huge variation depending on the pK values. It's all weak. Some of them are stronger than others. These are stronger weak acids, and these are very weak acids. Even on the weak acid scale, you have a huge range. These are stronger weak acids, and these are weak acids. So on that scale, you'll have the weak acid dissociating, and the base, the stronger base, then getting protonated. So that's your reaction because we know these values. So we will say this is number 1 and number 2, and if you add, just like we did before, you add the two equilibria, 1 plus 2, and you are going to get acetic acid, CH3COOH, plus you will have your base here, and that is going to give you, and here you would also put H2O and H3O plus, and you will see that is going to be gone. Well, let me write that down, H2O, just to make it complete, plus H3O plus. And here, when it goes over here, let's add these two. You are going to get ethanol, which gets protonated by the acid, plus the deprotonated acid, plus again H3O plus and H2O. You can see we can cancel these off. Therefore, you're only going to have the weak acid and base giving you a weaker base and a weaker acid. So that's always going to be the direction of your equilibria. So K equilibrium is this. So let's talk about this in terms of pKa values. So therefore here, this is going to be Ka1, this is 1 over Ka2. So when you add the equilibria, you multiply the equilibrium constant. That's something that you know from before. So K equilibrium is going to be Ka1 times 1 over Ka2. That is K equilibrium. Because we are talking about two different systems here. Now this, if you do the pKa of this, so this is going to be pKa1 minus pKa2, because this is 1 over, is going to be pKw. Now, if you want your pKw over here for a system, you don't really have to write up all of this. You write out the stronger acid, or the one on the left, minus the weaker acid, and that should give you the pKw. So you really don't have to do all of this. You only need to know this. And whenever you write down a equation like this, let's say HA1 plus A2 minus gives you A minus 1 plus HA2. If you have two acids in a system, just like this equation says, K equilibrium for this would be based off of this Ka1 and Ka2. So K equilibrium is going to be Ka1 over Ka2. We can also say this in terms of pK equilibrium, taking the negative log of this. So pK equilibrium, and I write this here, is going to be pKa1 minus pKa2. Now, the way we write this equation, we're always going to write the acid on the left-hand side, and the conjugate base is going to get protonated by that, and it's going to give you the weak acid on the right-hand side. Stronger acid will be on the left, and the weaker acid is going to be on the right. That's pretty much how you write it. So here you want this to be on your left and this to be on your right, the way it's written. So what is the K equilibrium for this equation? Just the acetic acid getting deprotonated by the ethoxide to give you ethanol and acetate. The equilibrium constant for that is going to be, for this reaction, it's going to be K equilibrium is going to be 4.8 minus 16. So that is going to be 11.2, negative. Is that a good thing to have a negative pK equilibrium? Well, we know just like you do pH and H plus concentration, taking the anti-log of the pH is going to give you the H plus concentration. It's the same thing here, 10 to the negative pK whatever is going to be giving you the actual value of that K equilibrium. So here you can see this is K equilibrium is going to be 10 to the negative 11.2, which is about 10 to the positive 11.2. So this is a huge number. So that means this reaction is going to go like a shot. So K equilibrium is almost more than almost like a trillion times more on the equilibrium is going to lie on this side. So if you have a very positive K equilibrium, that means your equilibrium is going to lie mostly on the right. All of your starting materials are reacted, and you're going to get mostly product thermodynamically. Okay, I don't know whether it's fast or weak, because K equilibrium doesn't really predict the speed. It's only the kinetic K that predicts the speed. But here we can see the equilibrium is going to lie over here mostly. Let's try this out. See if it works. Let's take any two systems. You can take this carbon, and let's say we take this nitrogen next door. Which way is it going to go? Is it going to go in this direction or in the opposite direction? So we have two acids here, this and this. We can write them any way we want, but let's say we write it out like this. H, let's say we take this molecule. And then we can add this base into it, which is the NH2 minus base. So it can go this getting protonated by this, because this is your minus, and this hydrogen can come off like that. That's one possibility. So you have here a protonated amide, which is ammonia, and you will have your conjugate base. So the question is it going this way or this way? Which way? And for that, we got to predict the K equilibrium. So what we do here is first identify your protonated species. Those are the acids. There are two protonated species. One is this, and the other one is this. So there are two acids. So this is your acid 1, and this is your acid 2. I'm just putting different colors. And we have pKa values for these. Your acid 1 is 25, and your acid 2 is 38. So this is pKa is 38, pKa is 25. So what's the K equilibrium? Just plug it in here, that's all it is. And the way it's written, we don't know whether the K equilibrium at this point is greater than 1 or less than 1. So just plug it in just the way it's written and see if you get a positive or a negative number. And then we can go from there. And we just blindly apply this equation. pK equilibrium is going to be pKa of the left acid and subtract the pKa of the right acid. Now here, the equilibrium can go this way or this way. We don't know. We're just going to find a number and then predict which way. So here this is going to be 25 minus 38, and that's going to give you a negative 13, which is, as we found out, a good thing in this case, because the equilibrium is then going to go to the right. Why? Because K equilibrium is 10 to the negative pK equilibrium, and so that is going to be 10 to the negative, and K equilibrium is negative 13, that is 10 to the 13. So that's a huge value. This is going to go, like completely almost to this side. Going to be hardly anything here. So this is a very nice way to predict whether something's going to go left or to the right. Let's do another example just to drive this home. Let's say I take some acid here and some base here, and then put it all together. Let's say here's sulfur and an oxygen. So let's say I take the alcohol here and add to a, let's go with this, RS minus. If there is a minus, obviously there's got to be a plus, right? And so then what are the protonated species? This OH is a protonated species. And here, when you take this off and go over here, this is going to be your protonated species as well. Plus, this is deprotonated. So the question is this going to go and deprotonate this and go here? Or is this going to deprotonate this and go here? We don't know. Let's put a K equilibrium value for this reaction. Because there is a reaction between these two. There are no other irrelevant molecules here. All of these are participating and they're in equilibrium. So the K equilibrium is going to be just the right-hand side over the left-hand side. Well, all we need to know is this going to be greater than 1 or less than 1? That's all we need to know to see whether it's going to go to the right or left. So then we can just blindly plug it into this equation. pK equilibrium is equal to the acid on the left. So we know acids are the ones that can release protons according to Bronsted definition, Arrhenius definition. So this is your acid 1. This is anions are typically bases. This is going to be again your protonated species. So this is your acid 2 that can release a hydrogen. So acid 1 and that's your conjugate base 1. Acid 2, and this is your conjugate base 2. So let's look at your acid. pKa is going to be over here 16. pKa left minus pKa right. And I have no idea whether it's going to go this way or this way. I'm just going to go on these numbers. So this is 16 minus 9.5. That's going to be 6.5. And that's a positive value. So K equilibrium is going to be 10 to the negative pK equilibrium. So that is going to be 10 to the negative, and this is a positive number, 6.5. So definitely lesser. This is, let's say, about almost 10 to the minus 7, or let's say, so it's almost like 0.0000. That small. The reaction is going to be almost entirely on this side. Whereas here, 10 to the 13, this is going to be almost entirely on this side. So you can predict the direction of the equilibrium based on the K equilibrium value, and that's based on the values of the protonated acids in the system. Well, just because I have space, let's do one more. Let's take the strongest base and the strongest acid and put them together. Let's take sulfuric acid and let's take this. So therefore, let's just do that for fun. Plus, and then the base here, I'm going to put CH3, CH2 minus. There's got to be some cation there. Any cation would do. I'm just throwing in a group 1 cation. So this is going to deprotonate this and give you CH3, CH2H plus, and this is going to become HSO4 minus. Just the first ionization here. So let's say this is going to be Ka1. First one has a Ka1, Ka2, and I can find out what these are. We're just dealing with pKa's because that's what the equation is, and we have it right here. So will this reaction go this way or this way? That's what we're trying to find. So let's do a K equilibrium here. pK equilibrium is going to be left-hand side acid minus right-hand side acid. pKa1 minus left minus pKa right. So that's going to be minus 9 minus 50. That is going to be huge. So that is going to be minus 59. That's huge. So K equilibrium is going to be 10 to the negative pK equilibrium. So that is going to be 10 to the negative 59. That's 10 to the 59. That's huge. It's like 10 followed by 58 zeros. That's huge. So that is going to be a very, 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 very large amount. Now, well, do you want to do this? Probably not, because look at what's going to happen when I calculate the delta G based off of that. Minus RT ln K equilibrium. So that is minus 8.314 joules per mole Kelvin times 298 times ln 10 to the 59. That's going to be a huge value. That's about negative 306,584 joules per mole. Huge amount. All right. So that's pretty much bordering on an explosion. So the worst thing that you could do is take some strong base and add it to a strong acid. It's going to go boom, blow up your lab. All right. That's, well, why? Because it's so much over here and it releases a huge amount of energy. The larger the K equilibrium, the larger the negative delta G. So all that energy comes out and probably brings your whole lab down. All right. So you can predict before you do an experiment whether it's safe, first of all. 2, is it really going to go? Why waste your time? Because you already have a table that gives you all the values. Check it out on the graph, on the chart. See if you're going to get a K equilibrium that's greater than 1. Okay, hopefully much bigger than that. Then you can go about doing the actual experiment and really getting some good results. So all of this is to help you determine if the reaction is going to go and which direction. And in summary, I just want to let you know that Ka values are really important in predicting the direction of acid-base reactions. Therefore, stronger the acid, weaker the conjugate base. The second concept is if you put 2 protonated species, let's say in water, what's going to happen? So here you're going to have an equilibria. And so the equilibria favors deprotonation of the stronger acid. The weaker acid would have a conjugate base which would be stronger. So the stronger base would deprotonate the stronger acid, and that's where the equilibrium will lie. So anytime you're given Ka values, you can always predict what direction the reaction is going to take, whether it's going to go forward or reverse. Talk to you soon, guys. Bye.